Educational Information and Communication Technology presents Educational Satellite Television Programs.
Hello, teacher. Hello, students. Welcome to today's lesson on alternating current. In our previous lesson, we reviewed the behaviors of sinusoidal waveforms within AC circuits and examined the concepts of reactance and impedance. Today, we will be looking at more complex circuit diagrams. If you are ready, we will begin. In our last lesson, we introduced an RC circuit, which makes use of a resistor and a capacitor. We looked at this circuit and managed to calculate its total impedance. Notice that a phase lead is present, just as demonstrated in our previous exercise. Many factors can affect this behavior, such as the voltage, current, and the relative strength of a circuit's components. Pictured here is a circuit with an inductor and a resistor called an RL circuit. In RL circuits, the waveforms are in phase, and if the resistor and inductor are balanced against each other, there is likely to be little difference between voltage and current. The resistors keeps current and voltage in phase, and the inductor creates a phase lag. It is possible that the circuit will have a negligible difference between voltage and current. In this image, we have a circuit with an inductor and a capacitor called an LC circuit. The former opposes change in current, while the latter opposes change in voltage. This usually means there is a phase lead or a phase lag, depending on how much power is provided to either component. The waveforms oscillate very quickly. They are likely to increase and decrease hundreds of thousands of times within a second. Let us look at this process step by step. First, a charge will start to flow through the inductor, building up a magnetic field and reducing the voltage in the capacitor. In time, the charge on the capacitor will be gone, and the voltage across it will reach zero. Because inductors resist change in current, the energy continues, so it will leave the magnetic field, causing the energy level to decline. This current will charge the capacitor with a voltage of opposite polarity to the original charge. Eventually, the magnetic field will be without charge. The capacitor will hold the charge instead. Because of the change in polarity, the current begins flowing back in the other direction, and the cycle restarts. As long as the circuit retains power from the source, it will continue to oscillate back and forth. The motion of current is similar to a pendulum swinging back and forth. This is called harmonic oscillation. If we isolate the circuit's resonant frequency, the circuit will conduct extremely well. This is why LC circuits are commonly used in radio tuning. Radios use resonance to tune the receiving circuits to the broadcast frequency of the station being tuned in. When a receiver is in resonance with this frequency, it is in tune with that station. Students, let us take a moment to make sure we properly understand the concept of LC circuits with an activity. Which of these objects do you think would make use of an LC circuit property?
Students, let's get ready. Begin. Time's up. Let's get back to our lesson.
Welcome back, students. The only incorrect answers are option D, a street lamp, and option E, a computer monitor. The other objects on this list use some form of LC circuit. Televisions, for instance, require a change in resonant frequency to alter the audio channels we hear as we change stations. Street lamps and computer monitors, however, use an RC circuit to manage flow of energy. LC circuits are largely theoretical in nature. This is because a circuit is always guaranteed to lose a charge to resistance over time. Just like a pendulum, the swing of energy back and forth will decrease over time until the voltage and current have been drained. An RLC circuit will resonate in the same way as an LC circuit. In an RLC circuit, however, the oscillation we create will eventually die out over time because of the resistance generated by adding a resistor to the circuit. It is a better example for the objects we introduced earlier in the lesson, since it takes into account any resistance created from a loss of power. This is the phasor graph that defines an RLC circuit. We can derive some important facts. Inductive reactance is the amount by which an inductor impedes the flow of current. It is given by the expression XL is equal to 2 pi times F multiplied by L, where F is the frequency of the supply's phase difference and L is the value of the inductance. Capacitive reactance is the amount by which the capacitor impedes the flow of the current. It is given by the expression XC is equal to 1 over 2 pi times F times C, where F is the frequency of the supply's phase difference and C is the value of the capacitance. If the inductive reactance is greater than the capacitive resistance, the phase angle is positive, so current lags behind voltage. If the inductive reactance is less than the capacitive resistance, the phase angle is negative. Thus, current leads voltage. If inductive reactance is equal to capacitive resistance, the phase angle is 0, meaning the reactance in the circuit matches the resistance. When this is the case, the circuit has found its resonant frequency. LC circuits and RLC circuits have a resonant frequency which is expressed as frequency is equal to 1 over 2 pi times the square root of inductance multiplied by capacitance. Based on what we have learned, let us answer this question together. Will an RLC circuit maintain its resonant frequency if electrical inductance is equal to electrical resistance? Why or why not? Take a few minutes to discuss with your classmates.
Students, let's get ready. Begin. Time's up! Let's get back to our lesson.
Welcome back, students. To answer our question, the RLC circuit will not maintain its frequency because the resistance created by the resistor will cause the resonant oscillations in the circuit to grow further apart. When a resistor behaves this way, it is called damping. Students, today we have learned a valuable lesson on the behavior of RL, LC, and RLC circuits. I trust you will find this information useful to your studies. Until next time, thank you, teacher. Thank you, students.